Here's the uncomfortable truth about today's smartest AI models: they're incredible at generating answers, but terrible at checking their own work. You ask an LLM to solve a hard math problem, it might get it right. But ask it to verify its own solution, to catch its own mistakes, and it falls apart. It's like a student who aces every exam but can't grade their own paper. That blind spot has been the single biggest bottleneck holding back test time reasoning. And this week, the research community responded with what might be the most important cluster of breakthroughs we've seen all year. Let's dive into what happened in week 22 of 2026, the week reasoning and reinforcement learning for LLMs finally started growing up. The verification bottleneck. Here's why this problem is so fundamental. When you give a language model more time to think at test time, letting it generate chains of reasoning, sample multiple candidates, search for better answers, the gains are directly limited by how well it can tell a good answer from a bad one. If your verifier is weak, you're just generating more wrong answers faster. A paper out of MIT and Cornell, Self-Trained Verification, or STV, pinpoints exactly why. A model can't catch its own errors in isolation. But here's the twist: it can when shown a reference solution. Think of it like a proofreader who needs the original manuscript open on the desk beside them. The paper trains a verifier that imitates a more informed version of itself, one that's seen the right answer. The results are striking: accuracy doubles on hard math problems. Scientific reasoning jumps from a baseline of 1.5% to 21%. And when you put that verifier into a loop, checking and rechecking during generation, you get another 33% improvement in pass at 1. What STV tells us is that self-verification isn't about being smarter, it's about having the right context. The model already knows how to judge correctness. It just needs to be prompted to use that knowledge. Smarter sampling, not more sampling. The second big theme this week: how we allocate compute during test time search matters enormously. A lot of current approaches use uniform random cuts, generating candidate answers, trimming away pieces, resampling. But there's a fundamental flaw in that strategy, exposed by Felix Zhu in their Entropy-Cut MCMC paper. The flaw is simple: most tokens in a generation aren't decisions. They're just local details, word choice, phrasing, formatting. The actual decisions, the points where the model chooses between fundamentally different reasoning paths, are rare. And if you're sampling uniformly, you're wasting compute rewriting the local details over and over while leaving the big decisions untouched. The solution uses next token entropy as a proxy, a thermometer for uncertainty. Where the model is highly uncertain about what comes next, that's a decision point. Where it's certain, that's just decoration. By targeting cuts at high entropy positions, the mixing time, how long it takes to explore meaningfully different solutions, scales with the number of actual decisions, not the total number of tokens. And the result outperforms RL-trained models on math, GPQA, and AIME benchmarks. No reinforcement learning required. Reasoning without chains of thought. This next one challenges a core assumption. Lucas Hberger and Sepp Hocrater's reasoning in memory, RIM, asks a provocative question: do you even need autoregressive chains of thought at all? Their architecture replaces the long chain of intermediate tokens with fixed memory blocks processed in a single forward pass. No, let me think step by step, just a compact representation that encodes the reasoning path. And it matches or exceeds traditional latent reasoning approaches. If this holds up, it could fundamentally change how we think about compute budgets at inference time. Less chatter, more signal. Scaling code generation without ground truth tests. CoSPlay from Zhang who addresses what's been a silent crisis in code LLMs. You can scale test time compute all you want, but if you don't have ground truth tests, you can't tell which candidate solutions are actually correct. And ground truth tests are expensive to write. CoSPlay's insight: let the code and the tests co-evolve. Two populations, solution candidates and test candidate pools, grow together through cooperative self-play. The tests get harder as the code gets better. On Qwen 2.5-7b, best of n sampling jumps from 22.1% to 33.2%. No external data, no human labels. Just structured competition. RL data at scale. And finally, R's automated rubric-enhanced synthesis. Xiaoyuan Li's team figured out how to automatically construct rubric-annotated reinforcement learning data at scale from raw documents. 100,000 training instances across 10 domains. This isn't just another data pipeline, it outperforms continual pre-training, supervised fine-tuning, and standard binary reward RL across the board. The secret is the rubric structure. Instead of a simple right-wrong signal, the model gets fine-grained feedback on which part of the reasoning went wrong. What this all means. Look at what these 5 papers share. None of them are about making models bigger. None are about collecting more human data. Every single one is about getting more out of the compute you already have: better verification, smarter search, compact architecture, self-play, and automated reward.